Okay, in this example, here is another example in which we are going to plot the Bode plot and the magnitude and the phase plot of this whole function. So the first thing first is convert this whole equation into this standard form, and in the standard form you can say that this is 0.4 into 1 plus j omega by 10. If you're going to take n common over here over j omega, and if you can take 5 and 5 because it's a square, so 25, so n over 25, so it will it will be 0.4 1 plus j omega by 5 square. So now the h dB, so the magnitude of this transfer function, it will be 20 log 10 of 0.4 plus 20 log 10 of 1 plus j omega by 10 minus 20 log 10 of j omega, the magnitude of this one, minus, and this is a square term, so minus 40 log n of 1 plus j omega by 5, because this whole 2 to 2, when it will be multiplying with 20, so it will be minus 40 as well. Okay, so this is the magnitude equation. And for the phase equation, so the angle of this one is 0 degree plus tan inverse of omega by 10 minus, so the angle of this pole at origin, it is minus 90 degree, so minus 2 tan inverse of omega by 5. So whatsoever is the angle is, you have to multiply it with 2, because they are two poles on the same location as well. So these two equations will be used to plot this whole thing. So now I'm going to plot the magnitude and the phase individually, and then I'm going to add them. Okay, first thing first, so we have a constant term over here, so log 10 of 0.4 multiply by, so you can multiply it to 20, so you have a state plot at minus 8 EB. You have a state plot at minus 8 EB. Okay, then you have a 0 at n, so from 10 to 20 you have a 20 degree increase, and so on and so forth, and it will remain at 0. So this is 20 log 10 of 1 plus j omega by 10. Now you have a pole at origin, so it will gonna start from here. In every decade it will gonna increase it down, and from previous decade, so you will have something like this one, and so on and so forth. So this is the integrator, which is minus 20 log 10 of j omega, and you have two poles at 5. So you can see that you at 5 over here, from 5 till 50, and then 500. So you have a slope of from 5 to 50, you have a slope of minus 40 dB. So this whole term, this is minus 40 dB per decade, and so on and so forth. So there are two poles at 5, so each pole will be adding minus 20 dB, so the total will be in a decade, it will be minus 40 dB. So now I'm going to add all them up. So add 0.1, so you have a value equal to -8 and 20. So you will gonna start it from my positive 12. So positive 12, so you will start from this point, and at 1 you will have -8 and the other one is 0. So you your final answer will be -8 as well. So at 1 you will have a slope something like this one. Okay, now again it will be down until 5, which will be minus 20 dB. So it will be keep on increasing. So the slope of this whole line, it will remain at minus 20 dB per decade until 5. And here you have from 5 it will be minus 60 dB until you will reach at 10, because one slope is minus 20 dB at 5 until 10. You have a slope of minus 20 dB over here and minus 40 dB over here. So the total slope will be minus 60 dB per decade. And from 10 and so on, the slope, now it will be, and you will add an increasing slope. So slope of minus 20 dB and one slope of positive 20 dB. So from 10 onwards, this slope will be minus 40 dB per decade, and so on and so forth. So this at the line, it is the final magnitude plot. Similarly, you can have a phase plot as well. So one is 0 degree, other one is minus 90 degree, and this one, it will start from 10. So from here till here it will be keep on increasing, and on 100 it will reach at 100. It will reach at positive 90, and then it will remain at positive 90. So this is the phase plot of is 0, this is minus 90, and then you have 2 at 5. So basically once you can say this is 5, so this one will be 0.5, this one will be 50, and this one will be 500. So I can say that from 0 till here you will have this one of 1 is this one, but you have 2 over here. So on 5, from 0.5 you will reach basically on minus 90, because you have 2. So one will reach at minus 45, the other one is also reach at minus 45, so minus 90, and on 50 you can reach on minus 180, and then it will be straightforward. Now I'm going to add all them up. So one is this straight line, the other one is this one, and the third one is this one. So you are going to add these 3. So it will start from minus 19 until 0.5, and then it will decrease from 0.5 till 1 with a ratio of minus 90 degree per decade. And from 1 you have a positive and 2 negative, so you have a slope of 45 degree per decade until 180. So this slope, it will be minus 45 degree per decade, and at 50, so all will be 0. So you will have a dip over here until 50, and then it will be a straight line over here. So you have 45 degree per decade over here, and then it will be all together, it will be stabled at some angle. Okay, let's take another example. This example we have represented in the form of S, and as you know that S is equal to j omega, so you can also represent it into the form of j omega as well. So it is in this way. So I can say that my h of omega, it will be 1 over 100, because if you can take 100 out, so 1 plus j omega over 1 plus j omega 6 by 10 plus j omega by 10 whole square. So this is the transfer function which we are going to compute. So its magnitude HdB, it will be equal to 1 over 100. If it is 1 over 100, so you can see that this is minus 20 log 10 of 100, because 1 over 100 means 100 power minus 1, so you can take negative sign over here, plus 20 log 10 of 1 plus j omega, and minus 20 log 10 of 1 plus j omega 6 by 10 minus omega square by 100. So this is the equation of the magnitude. And for the phase, so the angle of this constant term, it will be 0 plus tan inverse of omega minus tan inverse of omega 6 by 10 over 1 minus omega square by 100. So this is the equation. So now I'm going to plot them, because for this whole constant term, so log 10 of 100, it is equal to 2. So 2 multiplied by minus 20, so it will be at minus 40 dB. You have a straight line over here, and this whole term you will have 0 at omega is equal to 1, because this is j omega over 1, so the value of z is equal to 1. So 1 plus j omega over 1, so it will start from 1 and 10 and so on and so forth. So it will be a 0 up till here, and it will be keep on increasing. So this is a positive 20 dB per decade. Okay, and one line is this one, and the other one is this one, and then you have a quadratic term or the quadratic poles. So for the quadratic poles, it will, the omega n it is equal to 10 from omega n until 100, it will reach minus 40 dB and so on and so forth. So this is minus 40 dB per decade. So now I am going to add all them up. So at 0.1, you will start from minus 40 until 1, and from 1 to 10 it will be come up at minus 20. So this is basically positive 20 dB per decade. And from 10 to onward, it is minus 40 and plus 20. So this is a straight line, so minus 40 plus 20, so it will be minus 20 dB per decade. So this the red line, it is the magnitude plot. And now for the phase, you have a 0 and you have a omega over here, and omega is equal to 1. So from this is angle 45 degree positive, this is minus 45 degree, minus 135 degree. So from here to here, then at 10 to reach at 90, and it will be 90. So this is basically tan inverse of omega. And the other one, it is minus tan inverse of, so it will start from so at 10 it will be 90, and at 100 it will be 100. So this will be the slope of your tan inverse of omega 6 by 10 over 1 minus omega square by 100. So now I'm going to add these two. So my final answer, so it will be same until here, and then I have a dip because it is increasing, and this one is decreasing. I have a dip over here, and after that it will become stable, but this is again stabilizing, so it will end up to be on 100, on minus 90, and then it will be a stable one. So this whole plot, it will be the final phase plot of your given function. So I'm going to solve one final example now. It is the inverse example. The inverse example is, in this example we are given with the Bode plot, and from that Bode plot actually we need to find out the transfer function of the system. So we need to compute what is the equation of this function. So for that